So good morning, everybody. So the aim of this talk, in fact, is to explain the principle of the laser optical feedback imaging, and also to explain how the sensitivity and also the signal-to-noise ratio of this method can be increased by using acoustically tagged photons. So yes, this work is carried out in the laboratoire interdisciplinaire de physique in the University of Grenoble. And the result, which will be presented here, is the work of different PhD students, Arnaud Witomski, Wilfried Glatre, and more recently, Vadim Girardot and Carolina Goloni. So the outline of this talk are the following. Firstly, I would like to explain you the principle of the Lofi method, which is based on the high sensitivity of laser to optical feedback. Secondly, I would like to explain how it is possible to extract a synthetic aperture image from the Lofi signal to obtain a high-resolution imaging setup. Thirdly, I would like to explain how it is possible to increase the sensitivity and also the signal-to-noise ratio of our Lofi setup by using acoustically tagged photons. And finally, I would like to give you some perspective of how it is possible to use the Lofi vibrator to detect acoustic wave generated by photoacoustic effect. So to start, Lofi means laser optical feedback imaging. And here, for example, you have a direct comparison between an heterodyne confocal microscope, which is a Michelson interferometer, and here you have our Lofi microscope. And the main difference between these two microscopes comes here from the beam splitter orientation, the beam splitter orientation here, and the beam splitter orientation here. For the confocal microscope, the light which is reflected by the object is also reflected by the beam splitter and goes directly to the detector. While with the Lofi microscopes, the light which is reflected by the object is frequency shift, goes inside the laser cavity, and inside the laser cavity you have a beating between the feedback electric field, which is frequency shifted, and the electric field inside the laser cavity. So inside there is a beating. This beating is amplified by the laser dynamics, and it is this beating which is observed through the beam splitter inside the detector. So as you can see, this interferometer is self-aligned due to the fact that the laser is the source and also the detector of photon, in fact. And in this interferometer, the reference arm is the laser cavity itself, in fact. So there is no complex alignment. This interferometer is self-aligned. If you want to build a Lofi microscope, you need two things. The first thing is you need to use a good laser, and a good laser is for the dynamical point of view is a class B laser, and a class B laser is a laser which exhibits recession oscillation. Here you can see the temporal evolution of the laser intensity when you start the laser, and you can see recession oscillation. And in the Fourier space, the Fourier transform of this time evolution, you can see the resonance frequency, which is called the relaxation frequency, which is in the megahertz range. So the first thing, we need a good laser. This laser is a class B laser with a resonance frequency in the megahertz range if we use a microchip laser. If we have used here a diode laser, the relaxation frequency is in the gigahertz range, but it's the same principle in fact. So the resonance frequency is in the megahertz. The second thing is to use a frequency shifter here, and our frequency shifter is composed of two acousto-optic modulators. In fact, the first one with an acoustic frequency of 80 MHz, and the second one with an acoustic frequency of 81 MHz. And with to obtain a difference of frequency, 81 minus 80 MHz, to obtain a different frequency of 1 MHz, and this frequency is near the resonance of our laser dynamics, in fact. We can tune this frequency, and most of the time we work very near the resonance of the laser dynamics. So two things, a laser and a frequency shifter to build a Lofi microscope, in fact. So you can see an equation which gives the output power, the contrast of the output power modulation. This contrast depends on the reflectivity of the target and also of the phase. This phase is proportional to the distance between the laser and the target. And here you have a parameter which is a kind of gain, and this gain only depends on the dynamical parameters of our laser, in fact. And our work is to increase this gain And to start, of course, we put the frequency shift equal to the relaxation frequency to work at resonance, in fact. And under this condition, the gain is very simple. This gain is given by this formula here. This is the pumping parameter here. And the pumping parameter is normally equal to 2 or something like this. And here you have a damping rate ratio, in fact. This is the damping rate of the cavity divided by the damping rate of the population inversion of our laser. And we have found a laser, which is so you have a comparison with the heterodyne signal. So the same thing, the reflectivity of the target, the phase of the signal, and the main difference comes from this gain here, which is due to the laser dynamics, in fact. And with our microchip laser, the pumping parameter eta is equal to 2, and the damping rate ratio is equal to 1 million. So for feedback reflectivity equal to 10 to minus 12, the square root is equal to 10 to minus 6, the product of this and this is equal to 1, and therefore we have an output power modulation contrast which is equal to 100% in fact. So it is very easy with this kind of laser to detect a very small reflectivity in fact. A reflectivity of 10 to minus 12 gives us a very strong modulation of the laser output power in fact. So with this sensitivity we have tried to obtain different kind of imaging by the detection of this parameter, amplitude imaging, or by the detection of this parameter, this one, and this phase imaging in fact. Just to see a typical experimental setup for long range measurement, this is a very simple experimental setup. The laser source is here in fact. The beam filter is inside this black hole here, the photodiode is here. Here the two acousto-optic modulators to obtain the frequency shift. A reflection here. Here you have a telescope to obtain a small focal spot at a longer range if you want to do long range measurement. And here a scanner composed of two galvanometric mirrors to scan the laser beam on the target. So again, we only need a source and a frequency shifter composed here of two acousto-optic modulators. The first application is assistance for road traffic. This is an example. And in this experiment, we image a roadside located 40 meters away from the laser through a turbine media, which is composed of milk and water inside a glass tank. And in fact, the glass tank is very small, and the glass tank is only located on the left side, of the roadside. The scattering media is very dense. As you can see, it is impossible to see my hands through this media. And with our LOFI setup, you can see here the result, in fact. We are able, by detecting the small amount of photons coming back inside the laser cavity, to see the number 1, which is written here on the left. It is impossible to see the number 9 due to the boundary of the glass, the surface of the glass tank. And also, as you can see, it is impossible to see the letter M due to the fact that in the air, the amount of photons coming back inside the laser cavity is too important, and the laser is completely saturated. It is impossible to the laser to make the difference between the black and the white. In fact, the amount of photons is too important, and the laser output power is completely saturated, in fact. So this is an example for the detection through turbine media with our simple interferometer, in fact. Another experiment for vibrometry is here we try to detect a crack in a concrete structure. Here the concrete structure, you can see the front side of the concrete structure. Here you can see the back side of the concrete structure. And as you can see, there is here there is the crack. And this is a non-emerging crack due to the fact that the crack is visible here in the front side. The concrete structure is excited with a loudspeaker at 150 Hz. And with our LOFI setup, with our LOFI vibrometer, we have make a measurement of the amplitude of the vibration in the surface of the front side, and now you can see the result. And clearly, on the front side of the concrete structure, we are able to detect there is a difference of the amplitude of vibration on both sides of the crack. So with this simple interferometer, again, we are able to detect a crack in a concrete structure with a very simple experimental setup. Now a few words about the sensitivity of this setup. So this is the rate equation of the electric field of the laser inside the laser cavity. Here the stimulated emission. Here the damping rate of the cavity. Here the beating which is the LOFI signal before the amplification. And here the quantum noise, which is characterized by Langevin force. The experimental condition, it is an laser output power of 10 milliwatt, very small output power, an effective feedback reflectivity of 10 to minus 11, and the lock-in has an integration time of 1 millisecond. And if we look at the power spectrum, of course the LOFI signal exhibits a resonance at the relaxation frequency, but in the same time the laser quantum noise exhibits a resonance at the relaxation frequency. And if the laser noise is above the detector noise of the photodiode, the signal-to-noise ratio is simply given by the ratio between the blue curve and the green curve here. And as we can see, the signal-to-noise ratio is in fact frequency independent in this condition. And we can demonstrate that the signal-to-noise ratio is simply given by the shot noise limit in this condition. So a signal-to-noise ratio equal to 1 corresponds to 1 photon coming back inside the laser cavity during the integration time of the locking amplifier. In fact. Another example, here the LOFI gain is equal to 10 to 5. If you lose a laser with a smaller LOFI gain, for example 10 to 3, now the signal exhibits the same resonance at the relaxation frequency. The noise exhibits also a resonance at the relaxation frequency. But as you can see here, the laser quantum noise is above the detector noise only near the relaxation frequency. And under this condition, the signal-to-noise ratio here is a ratio between the blue curve and the green curve. This is here, and this is the shot noise limit. And here the signal-to-noise ratio is given by the ratio between the blue curve and the dark curve, and we are here. So if we want to be at the shot noise limit with this kind of laser, with a small gain, we need to work really near the relaxation frequency to have the laser quantum noise which is above the detector distance. So the shot noise limit is here. So experimentally we work clearly near the relaxation frequency. An experimental confirmation, this is the signal-to-noise ratio of our LOFI interferometer versus the effective feedback reflectivity. The measurement corresponds to the green square, and the shot noise limit is a red line. And as you can see, there is a good agreement. And here, for example, we have obtained a signal-to-noise ratio of 1 for a feedback reflectivity of 10 to minus 14. And as already mentioned, this is the signification. This signal-to-noise ratio equal to 1. This is 1 photon which comes back inside the laser cavity during the integration time of the lock-in amplifier. As you can see also here, there is a saturation. This saturation is due to an effect of the non-linear laser dynamics. Here you have an effect of linear laser dynamics, the beating frequency, the relaxation frequency, and here due to the non-linear laser dynamic, you can also observe harmonics of the frequency shift and so on. And this non-linear dynamics explain this saturation. So here you can see an example of the dynamical range of this experimental setup. In fact. So to summarize a little bit this part about the principle of LOFI, laser optical feedback imaging, the first advantage is that LOFI is an interferometric setup which allows amplitude and phase imaging. Another advantage is that the LOFI setup is auto-aligned due to the fact that the laser is the source and also the detector of photon. So there is no complex alignment to do. The LOFI also is shot noise limited due to the LOFI amplification gain, which allows to have a laser quantum noise which is above the detector noise. And there is one drawback. The drawback is due to the fact that to obtain an image is obtained point by point, line after line, so it takes a long time to obtain an image. For example, to obtain an image of 100 pixels by 100 pixels, roughly it takes 1 second or something like this. And this is due to the fact that the time response of our setup is the time response of the upper level of the laser transition, which is roughly equal to 100 microseconds for YAG laser, in fact. So the time response of the detector is the time response of the population inversion, in fact. So now I would like to explain briefly how it is possible to extract a synthetic aperture image from the LOFI signal. And to begin, I need to recall briefly what is the synthetic aperture process, which principally comes from the radar domain. So in the radar domain, if we define the radar initial position as the position where a punctual target enters into the diffraction spot. And if the diffraction spot is characterized by this diffraction angle, which is given by the ratio between the wavelength and the size of the radar source. Due to the radar scanning, due to the radar displacement, in fact, we can also define the radar final position as the position where the punctual target goes outside the diffraction spot. And between the initial and the final position, we are able to define a numerical aperture, in fact. And due to the displacement, due to the radar scanning, it is easy to see that the numerical aperture is equal to the diffraction angle. And now if we define the resolution as a ratio between the wavelength and the numerical aperture, we obtain a resolution which is given by the size of the source. So in this experimental setup, it is interesting to notice that we have a resolution which is only given by the size of the source. So the resolution is independent of the distance between the punctual target and the source, in fact. The resolution is constant, whatever the distance between the punctual target and the source. Experimentally, in fact, how does it work? In fact, the synthetic aperture process is simply, in fact, a correlation calculation between the reflected signal and an adapted filter, in fact. And for a single punctual target, the signal which is reflected by the target during the scanning of the radar is simply a chirp pulse, principally due to the Doppler effect. And the adapted filter in this situation is simply the time reversal of this signal. So the adapted filter is here. And to obtain the synthetic aperture signal, we need to make a convolution calculation between this signal and this signal. And finally, if we take the modulus, we obtain the synthetic aperture signal. And as we can see, we have obtained a time compression due to the fact that the time width here is smaller than the time width here. And this time compression allows to increase the resolution of our setup. So again, here, this is equivalent to the size of the diffraction spot. And here, this is the size of the source, which gives the final resolution, in fact. And now for a double punctual target, the time evolution of the reflected signal is much more complicated, but if we use the same adapted filter, we do the correlation calculation between this signal and this signal, and if we take the modulus, we obtain this signal when here now clearly the double punctual target is clearly resolved. Here it is impossible to see the double punctual target. Now here, due to the time compression, due to the increase of the resolution, it is possible to see the double punctual target. So now, I would like to explain how it is possible with our low-field microscope to extract the synthetic aperture image. So again, the low-field microscope, here the laser, the frequency shifter, and in this setup, the resolution of the image is given by the size of the focal spot on the target, on the object. And the image is obtained point by point by the scanning of the laser beam on the target. And now what happens if we move away the object from the focal point? And by doing this, we are now in the same experimental conditions than those previously mentioned when I speak about the radar. The radar source is here now. This is our focal spot. The diffraction spot is here. And the radar displacement is equivalent to the scanning of the laser beam on the target. So now, by doing this, the object is illuminated with a defocused laser beam, and we hope to be able to restore an image of this object with a resolution which is given by the focal spot here, whatever the distance between the object and the focal spot, in fact. So the first example here is a numerical simulation, in fact. The target under investigation is composed of 4 individual reflectors, and the distance between the reflector, of course, is smaller than the size of the defocused laser beam. And in the conventional low-field image, of course, due to the fact that the beam is completely defocused, it is impossible to see nothing. And after applying a 2D synthetic aperture process, we are able to obtain a 2D synthetic aperture image, which is shown here, in fact, where the 4 individual reflectors are clearly resolved. Another important thing, here you can see a 1D synthetic aperture image obtained after a 1D synthetic aperture process in the y direction, and here a 1D synthetic aperture image obtained after a 1D synthetic aperture process in the x direction. It is important to notice here you have 2 lines. due to the fact that also you see there is two lines, there are two different directions between the reflector and the laser, and these two directions correspond to these two lines. In this direction, there is three different vertical lines, and of course you see three different vertical lines. Also, you can observe the interference fringes here between these two sources. Here, the interference fringes between these two sources. Here, the interference fringes between these two sources. And here, no interference due to the fact there are only one source. So the synthetic aperture image is simply, it consists to extract information, in fact, from the interference fringes which are shown here, in fact. The second example here is an experimental verification of the fact that it is possible to extract a synthetic aperture image from the LOFI interferometer. And the target under investigation is composed of silica beads with a diameter of 30 micrometers. And the silica beads are located behind a P-shaped hole with a dimension of typically 1 millimeter in height and 1 millimeter in for the width. And we have obtained different images with this target. The first image is a conventional LOFI image obtained with a lens. The lens here has a high numerical aperture due to the fact that the focal length is very short. And with a lens with a high numerical aperture, of course, we are able to resolve the silica beads which are located behind the P-shaped hole. Now we move the object, and to obtain the conventional LOFI image, we have used a lens with a lower numerical aperture, with a longer focal length. And with this lens, with a lower numerical aperture, now you can see the image. Of course, with this lower numerical aperture, we are unable to resolve the silica bead. We only see the P-shaped hole, and with a speckle effect, speckle aspect inside. Now the object is always here. We take this lens with a high numerical aperture, in fact, and the focal point is in front of the object, and the distance between the focal plot and the object is equal to L. The conventional LOFI image is shown here. Of course, we see nothing due to the fact that the laser beam is completely defocused. And after the 2D synthetic aperture process, you can see the image, in fact. So now, again, we are able to restore, to resolve the different silica beads which are located behind the P-shaped hole. So by using this simple interferometer called LOFI, we are able to extract synthetic aperture image by simply using the scanning of the laser beam on the target. So it works, but there is a drawback, and this drawback is due to the fact that the number of photons which come back inside the laser cavity decrease proportionally to the square of L, and this is due to the confocal filtering of our microscope, in fact. But this drawback, in fact, is partially compensated by the LOFI gain, and also partially compensated by the fact that the LOFI is shot noise limited, in fact. So to summarize a little bit this part of my talk, so the LOFI setup with a focal spot here, the target is illuminated with a defocused laser beam at the distance L, and after the synthetic aperture process, the equivalent setup is shown here. We have the same focal spot here at a longer distance with the same numerical aperture, and the drawback is characterized by the optical density which is here. The formula for the optical density is given here, and is roughly proportional to the surface area of the defocused laser beam divided by the surface area of the focused laser beam, and this surface ratio is proportional to the square of L. So after the synthetic aperture process, the equivalent setup is shown here. A good resolution, but a small number of photons coming back inside the laser cavity. Now I would like to give you another physical interpretation of the synthetic aperture process. In fact, the raw image which is initially obtained in the LOFI setup, in fact, is a blur complex image of the target. As you can see, the image is this is the electric field of the image, and this is simply the convolution between the real image and the free space propagator, the Fresnel propagator. The formula of the free space, the Fresnel propagator is given here. So from this complex wave, this is a complex wave because with the LOFI interferometer we are able to record point by point, line by line, the wavefront of the feedback electric field. So we know the electric field, the amplitude and the phase of the electric field. So by using the free space propagator, we are able to propagate back this complex wave to the image plane. This is equivalent to the time reversal. In fact, I speak about a little bit of the starting, but now we propagate back this complex way to obtain the synthetic aperture image. And here you can see an experimental confirmation of the numerical refocusing. In fact, at the beginning, a small filter mismatch, and the filter mismatch decrease. We reach the adapted filter, and when the adapted filter is reached, of course, we have obtained the synthetic aperture image, in fact, where the silica beads are clearly resolved. So, in fact, our synthetic aperture image is simply a numerically refocused image, in fact. So, another example of numerical refocusing, but now on the curved surface. So now the target under investigation is a flexible tissue with silica beads on its surface, and the tissue is voluntarily curved to obtain, in fact, a 3D object. The conventional LOFI image, the raw image, the blurred complex image obtained from the direct LOFI signal. Here you can see the image after a numerical refocusing in an intermediate plane, and as we can see, only a small part of the beads are flat, due to the fact that only a small part of the image is well refocused, in fact. And here you can see the best refocusing surface after scanning in a different plane. And here you can see the silica beads located on its surface. So in fact, our synthetic aperture LOFI setup is a kind of plane optic microscope, in that by using a 2D scanning, we are able to obtain a 3D, in fact, a 3D image, in fact, by using simply a 2D scanning, and by using numerical refocusing. Another example, the target under investigation is always composed of silica beads, and in this experiment we have voluntarily introduced aberration in our setup. The lens which is used is the plano-convex lens, which is voluntarily tilted to introduce aberration, in fact. So the raw complex image obtained with the conventional LOFI setup, the image which is obtained after simple numerical refocusing, and the image which is obtained after numerical refocusing and the compensation of the coma and astigmatism aberration, in fact. And here the final image without aberration. And here you can see an example of the point spread function, where we can see the aberration which are initially present in our setup. These aberrations are corrected to finally obtain a very good image at the end. So again, from the complex wave, it is possible to numerically eliminate aberration in our setup. So to summarize this part, so the synthetic aperture LOFI is simply the combination of the high sensitivity of the LOFI setup and of the high resolution of the synthetic aperture imaging. And perhaps it's also depth imaging through turbine medium with high resolution. Another advantage is due to the fact that the synthetic aperture LOFI is an interferometric setup which allows to record the wave front, and therefore numerical refocusing and numerical correction of aberration is possible. And one drawback already mentioned is due to the fact that the number of photons coming back inside the laser cavity is very small, but this drawback is partially compensated by the gain of the LOFI setup, and also due to the fact that the LOFI measurement is shot noise limited. So it is possible to obtain a synthetic aperture image from the LOFI setup. Now the third part of this talk. Now I would like to explain how it is possible to increase the sensitivity of our LOFI setup, and also to increase the signal-to-noise ratio by using acoustically tagged photon. And firstly, I need to explain what is a parasitic echo in a LOFI setup. So again, our LOFI microscope is here, the laser, the frequency shifted, the target under investigation, and the target is characterized by its reflectivity RT and the distance dt between the laser and the target. And under this condition, the amplitude of the LOFI signal is given by the product of the laser output power, the reflectivity of the target, and the amplification and the LOFI amplification gain. And the phase shift of the laser modulation is proportional to the distance between the laser and the target. And if we plot, and for a small displacement of the target, if we plot this signal in polar coordinates, we can see what we call the LOFI circle, in fact, with a radius which is proportional to the amount of feedback coming back inside the laser in the laser cavity. But now, what's happened? If there is a parasitic reflection in our setup, a parasitic reflection coming back from the lens, coming back from the scanners, coming back from the output face of the frequency shifter. So if there is a parasitic reflection, what's happened in fact? And if we look at the LOFI signal with a parasitic reflection, what we can see a displacement of the LOFI of the LOFI circle. Sorry. Yes, and this displacement, of course, is due to the interference between the feedback electric field coming back from the target and the interference between the electric field coming back from the parasitic reflection. And as we can see, due to this interference effect, the LOFI signal depends, of course, of the target, but also of the parasitic echoes, both for the phase. The phase also depends of the target and the parasitic echoes, phase of the target and phase of the parasitic echoes. So now the question for us is how it is possible to separate the feedback signal and the parasitic echoes, in fact. And to do this, we have used acoustically tagged photons. So the principle is the following. Acoustic tagging the photon near the target, in fact, to shift the frequency of the photon coming back from the target by a frequency FA. So now we are able to make the difference between this photon and the photon we come back from parasitic echoes, where there is no frequency shift. And under this condition, the LOFI image are now limited by the photon noise and not by the parasitic echoes. And our experimental setup is the following. Again, the LOFI microscope with the laser, the frequency shifter, the laser beam is focused on the target. The target is inside the glass tank with this filled always with water and milk. And inside the scattering media, we have also used an acoustic transducer, which allows to focus an acoustic wave on the laser beam. So the light will come back from the target, can see the acoustic frequency, while the parasitic echoes coming back from for example, from the lens or from the mirror or from the input face of the glass tank are unable to see the acoustic frequency. So this is the principle of the acoustic photon tagging for us, in fact. Here's the equation for the signal-to-noise ratio of the LOFI setup with the parasitic echo, which are present here in the signal and also in the noise, and the signal-to-noise ratio of the acousto-optic LOFI when the acoustic photon tagging is used. And we have made the experiment where the parameter is given here, K-opt, is the ratio between the laser incident power of the target, so just here, divided by the total laser output power. And if we look at this, how the signal-to-noise ratio evolves versus K-opt, we can see a linear dependence of the acousto-optic LOFI due to this linear dependence which is here. And for the conventional LOFI with parasitic reflection, we can see this saturation, which is due to this, the division of this parameter by this parameter when K-opt is impact. So as we can see, we have obtained an improved SNR by using acoustic photon tagging, by using this acoustic transducer here. An experimental confirmation of this. The target here under investigation is a metallic ruler. The scattering media is composed of water and milk. Yes, you see inside the glass tank. The round trip losses are roughly equal to 50 dB for the round trip, in fact, and the frequency detection is made with a 3 MHz frequency shift for both imaging. So the first image, which is a conventional LOFI image, obtained without acoustic photon tagging. So we can see here a part of the metallic roller, and the noise here is due to parasitic echoes. And now if we use the acoustic photon tagging, you can see the acousto-optic LOFI image. Here's the metallic roller, and here's the noise now is due to the laser noise. This is the short noise limit. This is the laser. Quantum. This is the laser quantum noise. So as we can see, there is an increase of the contrast. Here it's very black or dark. We can calculate also the signal-to-noise ratio by dividing the signal in this square by the signal in this square, and again here, in fact. And here the signal-to-noise ratio is equal to 1.6, and here the signal-to-noise is equal to 5, in fact. So we have increased the contrast and also for the signal-to-noise ratio. And we have increased the signal-to-noise ratio even if the acousto-optic efficiency is only of 13%, in fact. So The acoustic efficiency is very low, but nevertheless we have obtained an increase of the signal to noise ratio in fact. It works also in for the synthetic aperture image. The experimental setup is roughly the same. The LOFI microscope now is focused here in the glass tank in front of the target plane. The acoustic transducer allows to focus an acoustic wave here on the laser beam. And for the detection, we have used a frequency mixer to make a detection at the difference between the frequency Fi minus Fa at 4.4 MHz. And to avoid any amplification due to the LOFI gain, the detection is made at the same frequency. So without acoustic photon tagging, the detection is made at 4.4 MHz, again here 4.4 MHz, but by using the combination of 8.9 MHz minus 4.5 MHz. Now the result, again, the raw complex image obtained at the beginning, the image after the synthetic aperture process without acoustic photon tagging and with acoustic photon tagging. Again, we can see here and here an increase of the contrast. And here we can see the effect of the parasitic echoes which generate this ring due to interference effect in fact. We have evaluated the signal and how the signal evolves when the density inside the turbine media increases, in fact. And as we can see here, this is this signal here, when the optical density inside the turbine media increases, the signal decreases. And after you have a saturation, and this saturation is due to the parasitic echoes. While with acoustic photon tagging here, of course the signal is lower due to the small efficiency. But as you can see, the signal decreases and reaches the limit, which is the shot noise limit, which is due to the laser quantum loss. So it is possible to go deeper in the media, in fact. So it works. So to summarize this part, I would like to say that acousto-optic LOFI allows to make the difference between parasitic echo and the feedback electric field coming back from the target under investigation, allows to improve the LSNR, allows to obtain amplitude images limited by photon noise. So this is the shot noise limit, and also in the synthetic aperture process, it is also possible to obtain images limited by photon noise. In fact. Now I would like to give you some perspectives about the use of the LOFI vibrometer for the detection of acoustic waves generated by photoacoustic effect. So our goal is to measure photoacoustic effect with a LOFI vibrometer and to make a comparison with a focused acoustic transducer for the detection. So again, the LOFI microscope is here. Yes, the laser, the frequency shifter, the beam, the laser beam is focused on the surface of the water. And for the generation of the acoustic wave, we have used a photoacoustic laser, which is pulsed. And the absorbing media is a tube filled with ink. To begin, I need to explain how it is possible to extract a good vibration from the LOFI signal. What is the signal processing to extract a good vibration? So the first step is to record, of course, the LOFI signal, which is a convolution between the beating and the impulse response of the laser dynamic. Of course, the impulse response of the laser dynamic is the inverse Fourier transform of the LOFI gain. So we go in the Fourier. Space. In the Fourier space, we only keep the right side of the Fourier spectrum in a small bandwidth or in a bandwidth around the frequency shift. And the most important step is here. If we want to restore the good shape for the vibration spectrum, we need to divide the spectrum by the LOFI gain. This is the most important step. After we come back in the temporal domain, and after there is a demodulation to limit the frequency, the initial frequency shift. And finally, we are able to extract the vibration measurement, the evolution of the phase during the time, in fact. Just the first example is a numerical simulation for the detection of an harmonic vibration. This is a small amplitude of vibration, 2p divided by 50. This is lambda over 100. The acoustic frequency is really equal to 300 kHz if the relaxation frequency is equal to 1 MHz, in fact. And the frequency shift is near the resonance, as we can see here. And two examples, this is a small feedback, 10 to minus I, and here a strong feedback, 10 to minus 7. The frequency shift is here, the two sideband induced by the acoustic vibration are here. Again, the frequency shift is here, the two vibration sideband induced by the acoustic vibration is here. And if we don't take into account of the gain compensation, this is the exact vibration in blue, and in red, the vibration which is extracted from our lofi signal without a gain compensation. In both cases, as we can see, there is a mistake. And now, if we take into account of the gain compensation, we are able to restore, with our lofi vibrometer, with our signal processing, the good vibration of amplitude, in fact. So it works for harmonic vibration. It also works for transient vibration. The same process, a strong feedback, 10 to minus 7, a broad spectrum equal to 300 kHz near the relaxation frequency. And here you can see, here you have different amplitude of vibration. As one can see, the exact transient vibration is a black curve. And with the circle, this is the vibration which is extracted with our, from the lofi signal with our signal processing. And as we can see, we obtain the good amplitude and also the good time delay if we take into account of the gain correction, which is the blue curve, in fact. An experimental confirmation for a transient harmonic vibration. In fact, the vibration target is a PZT, which is a switch off here, switch on here, switch off again, for different amount of optical feedback. Here you can see the linear gain, here non-linear gain, which will be compensated to obtain a good signal. And here the vibration which is obtained with an amplitude of 25 nanometer, and here with a noise of 2 nanometer. Here the noise is equal to 4 nanometer, and hopefully to 6 or perhaps 10 nanometer. So if we increase the amount of optical feedback, the laser dynamics become non-linear, but we are able to obtain a vibration with a smaller noise equal here to 2 nanometers, in fact. Just to finish, a confirmation, we have also, with our lofi setup, detect acoustic waves generated by a photoacoustic effect. Again, the laser is a pulse laser, the absorbing media is a tube filled with ink, and the lofi detection is made here, after here, after here, after here. And here you can see the vibration which is extracted with our interferometer. As we can see, we obtain here an amplitude of 4 nanometers. The noise here is approximately equal to 2 nanometers. And when the lofi detection moves from this point to this point, as we can see, there is an increase of the time delay, and also there is a decrease of the amplitude of vibration. The experimental conditions are the following. The laser intensity is 100 millijoules per square centimeter, no focalization. The absorbing media diameter is 1 millimeter, and for the lofi detection, the frequency shift is 5 MHz, and the bandwidth for the vibration detection is 1.3 MHz. So it is possible to detect small amplitude of vibration generated by photoacoustic effect with our lofi setup, in fact. And to conclude, the perspective actually, we try to detect the formation of aggregates of red blood cell in a micro vessel by using a photoacoustic setup with an optical resolution, and also by using a photoacoustic setup working in a frequency domain. This is a photoacoustic image obtained with this setup, and by using the light scan method, we try to detect the aggregate of red blood cells. You see, you have 2 red blood cells, and here the image obtained with the light scan method. And this method, of course, the slope of the line is inversely proportional to the speed of the red blood cell, and the size of this line is proportional to the size of the object inside the light scan. And actually, we are beginning to some experiment on the ear of a mouse to detect aggregate of a red blood cell, in fact. I think this is the end. Well, thank you for your attention.
We have time for questions.
So you're using scattering media and not multiple scattering media. If I understand well, you really need direct photon to reach the...
This is a current interaction between the feedback electric field and the electric field inside the laser cavity. And of course, we only work with the ballistic photon.
Okay.
Yeah. This is a current interaction.
I have a question on synthetic aperture LOFI.
Yes.
I don't know if I well understood. The synthetic aperture processing is a numerical image processing algorithm, or is it done by the optic setup?
No, it's a conventional numerical algorithm, in fact. In fact,
You find the LOFI image and after you process the image?
of course,
Okay.
everybody can use a microscope, defocus a little bit the target from the focal plane, and if you are able to record the amplitude and the phase of the feedback electric field, you are able to restore an image with a very good resolution, in fact. And of course, just to say that.
But it's faster. You don't have to do all the points. Just in one point you have all the
No,
information.
you need to scan, because at the beginning I explained you need of the radar displacement, in fact, to obtain the synthetic aperture. If there is no displacement, it is impossible to obtain the synthetic aperture process. In fact, just to we need here of this chirp pulse, in fact, and this chirp pulse for the convolution calculation is due to the displacement of the laser beam of the target, in fact. And if you know a little bit optic, in fact, this chirp pulse is a Fresnel free space propagator, in fact, with a quadratic phase, in fact. This is the same thing, in fact. So this is numerical refocusing, adapted filtering, this is the same thing, in fact, due to the fact that the Fresnel propagator generates a chirp pulse, in fact, in space or in time or what you want. But you need of a displacement, in fact.
And so you need numerical processing with the algorithms.
Yes.
To make the synthetic aperture.
But it's very simple, in fact. You take this signal. You take, for example, you don't know what is the adapted filter. In fact, you take the signal for the double punctual target. You make the Fourier transform, and the size of the broadband of the Fourier spectrum gives you the size of the adapted filter. In fact. In fact, of this course, when I do the Fourier transform, I have a spectrum, and there is fringes in the spectrum, but there is no importance. The size of the spectrum gives the size of the frequency shift of the chirp pulse, and it's enough, in fact.
Did you try other more performing algorithm from radar processing? We can see in the literature that this is the basis, matched filtering, but they can make motion compensation, they can make a lot of different things with just processing the original data.
Yes.
Which just make matched filtering.
The more simple, in fact.
Okay. Thanks again.